Hi everyone, and welcome to the second set of problem solving of numerical method. And this time the questions will be about linear equations. So we will have two questions. The first one is basically we have a 3 by 3 system and we want to solve for x1, x2, and x3 using Gaussian eliminations using the exact solution. So here we'll use fractions only. Then we will use the same method, but we'll use three significant digits. So we'll use decimals here without partial pivoting. We'll repeat the same thing, but with partial pivoting. We'll see if there is any difference. And then we want to calculate the exact relative error between B and C from the exact answer, which will be part A. So the first thing when we deal with this type of questions, we have to put the system of equations into an augmented matrix. So basically, we will have the 3 by 3 system. So here, these are the coefficients of the first row, the 3, 14, and 28, 1, 3, 3, 2, 6, and 10. And here at the end is the vector, the output vector. So now our first objective is to make this item and this item is equal to 0. So basically here we will have row 2, which is this row, minus the coefficient of row 2 divided by the coefficient of row 1 minus 1 over 3 times row 1. And then I want to make this also equal to 0, the 2 equal to 0. So we'll have it row 3 minus 2 over 3 row 1. So after I do the subtraction, I will get this matrix, but I will do it, as I said, in fractions, not in decimals. So now, first thing accomplished, this is all zeros. Now I want to make this element 0. Now I will not touch the first row. Now this is done. So basically it will be between row 2 and row 3. So this is, I'm just drawing this basically this matrix. So now I will have row 3 minus this coefficient, which is minus 10 over 3, divided by this coefficient, which is minus 5 over 3, times row 2. And if you do that, this is what you're gonna have. Okay, so this is now the matrix in the final form. Now I will start the back substitution starting from the third row. So basically here I will have 4 times x3 equal to minus 4. So from this, your x3 will equal to minus 1. Same thing, now we'll go for the second row. We'll have minus 5 over 3 x2 minus 19 over 3 x3 equal to 14 over 3. Now we know x3, so from this, your x2 will be equal to 1. And then we go for the first row. So if we go from the third to the second, and then from the second to the third, and every time we have only one unknown. If you solve for this, you will find that your x1 is basically equal to 2. So that is the first part. Let's do now the second part, which will be now, I will use decimal. I will use 3 significant digits. So again, we'll start with the same matrix, exactly the same thing. And I will start, or to be exact, the same procedure. So we have row 2 minus 1 over 3 row 1, and row 3 minus 2 over 3 row 1. This is exactly the same procedure. Now the output will be different here because now we have decimals and we have only 3 significant digits as stated in the question. So we are finished with this. Now we'll go for row 2 and row 3. And here comes the difference between partial pivoting and without partial pivoting. Without partial pivoting, I don't care about the order of the numbers, okay? Which one is higher, which one is smaller. And that is what we're gonna do. We'll see now when it comes to the partial pivoting, we will do some change in the order of the equations. So back, we will start from this, the same matrix. Then I want to get rid of this. So I will have row 3 minus 3.33 divided by minus 1.66 times row 2, and we do that, you will get that is my output now. Okay, now I am ready to solve for the equations now without partial pivoting. So basically you start from the back propagation. You will have 4.03 x3 equal to minus 4.01. And from this, your x3 will be equal minus 0.995. Okay, and then go and substitute the values, go from here to there. Now we have another one, oh no, we have minus 1.66 x2 minus 6.33 x3 equal to 4.66. So x3 is known to me. Solving this, you will get that your x2 is equal to 0.986. And finally, you solve for 3x1 plus 14x2 plus 28x3 equal to minus 8. And from this, you get your x1 is equal to 2.01. Now, have a look to these solutions and the exact solution, minus 1 compared to minus 0.995, 1 to 0.986, 2 compared to 2.01. So they are close enough to the solution, but if you want to get a better resolution, then we have to increase the number of significant digits. Now, let's do the same thing now, but I will consider partial pivoting. Okay, so going from this matrix to this matrix, this is exactly like part B, same, no difference. So this is like part B. Now the difference here, after you finish this, you look to the row 2 and row 3, you will find that the absolute value of the minus 3.33 is larger than the minus 1.66. And if there are some other rows, we'll compare all of them. And we'll bring to the top of the line in the matrix, the one that with the highest number. So obviously this is higher. So I will swap these two rows. So we will get this. And then we will continue. Okay, so now I wanna make this equal to 0, basically. So we'll have row 3 minus 1.66 divided minus 3.33 row 2, and if you do that, you will find this is the final answer. And if you compare this matrix with the previous one, you will see that we will end up having the same solution. So we'll have minus 2.01 x3 equal to 2.00. From this, you will find that your x3 is equal to minus 0.995, and you repeat this the same thing, you will find your x2 is equal to 0.986, and x1 is equal to 2.01. And here I'd like to make a comment that not always partial pivoting will give you a better result. In some cases, yes. In some cases, it will give you exactly the same answer as without partial pivoting. This is why, because we don't know how using the partial pivoting will affect the solution. Whenever we can apply it, we will use it. And finally, here we want to find the exact relative error here in these questions. Okay, so the exact relative error, so we actually are subtracting the true value, which is here. These are the true value from part A, and this is the approximate value for basically B and C. We are the same thing. So here you will find the exact relative error of x1. So it is equal to the true value, which is 2 minus 2.01 divided by the true value, okay, times 100. And this will give you minus 0.5%. This is the exact. So the exact relative error of x2 will equal to 1 minus 0.986 divided by 1 times 100, which is equal to 1.4%. And finally, the exact relative error of x3 will equal to minus 1 minus 0.995 divided by minus 1 times 100. And this will give you 4.5%. So this is the percentage errors between the approximate values and the exact value. As I mentioned earlier, if I want to reduce this error, then I have basically all I need to do is I need to increase the number of significant digits. Let's go for the second question, which is about using the Gauss-Seidel method for iteration. So we have here this system of equations. It's a 3 by 3 system. And basically, we want to calculate the values of x, y, and z after two iterations. Okay, and we are given here the initial conditions, and we want to see, does the system converge or it doesn't converge? And if it doesn't converge, how we can make it converge. So we'll start with the initial system. I will not do anything in it. All I need to do here is to redraw the equations. So I will have 3 equations, one in terms of x, and then y, and then z. So for example, here, it will be 2x equal to 5 minus 10y minus z. So your x will equal to 1/2 times 5 minus 10y minus z. And I will do exactly the same thing here. I will have everything in terms of y, and here everything in terms of z. So doing this, we'll have these 3 equations. Okay, and now we'll start the iteration. We'll start our first iteration. Now, the first iteration, we always use only the initial guess. So your x of first iteration, now all the values are 1, 1, 1. So it is 5 minus 10 times 1 minus 1 divided by 2. And this will give me minus 3. Comes here to the y for the first iteration equal to 1 minus, now x has an updated value, which is the minus 3. I will not use the 1 anymore. This is minus 3 plus 10. Now z, I don't have any answer for it. It comes equal to 1 divided by 2. And this will give me 7. And finally, your z first iteration will equal to 3 times minus 3 plus 7 minus 10, and this is minus 12. This is my first iteration. Now I will go for the second iteration. I'll see, is my answer start to converge, or it's clearly that it is diverging. So let's go for x of 2, and now we'll do the same thing. Now these are my initial guess or my initial iterations or solutions. So x2 now becomes equal to 5 minus 10 times y, which is, so it is, 5 minus 10 times y, which is 7, minus z, which is minus 12, divided by 2, and this will give me an answer of minus 26.5. If you go for y second iteration equal to 1 minus x, which is minus 26.5, plus 10z, which is minus 12, divided by 2 again, and this will give me basically minus 46.25. Finally, z second iteration will equal to 3 times minus 26.5 plus y minus 46.25 minus 10. And if you solve this, you will find this is minus 135.75. And clearly the system is not converging. And if you keep doing this, you will the number will start to increase. So what went wrong? The problem here, when you look to the diagonal elements here, they are not basically diagonally dominant, this matrix. What does this mean? that the coefficient of the first row, 2, the absolute value, has to be greater than or equal to the summation of 10 plus 1, which are the coefficients of the remaining of the matrix, and clearly that's not true. And if you go for the second row, the same thing here, 2, the 2 here is not greater than or equal the coefficient of x, which is 1, plus the coefficient of z with minus 10. And the same thing here for the last one. So for all the three rows, the matrix is not basically diagonally dominant. So we need to rearrange the matrix so that we will have a dominant matrix, and this is how. So these are the same equations. I put the third equation first, the first equation second, and the first equation third. Now when you look here to the diagonal of this matrix, which by the way, again, I did not change anything. I did not change the equations. I just changed their order. So easily here you can see that in the first row, your x, which coefficient, which is 3, is greater than or equal the 1 plus the minus 1. If you come to this equation, the 10, the absolute value of the 10 is greater than or equal the 2, the coefficient of x, plus 1, the coefficient of z. And lastly, also, the absolute value of the coefficient of z is greater than or equal to the coefficient of 1 plus the coefficient of 2 of the y. So in all the rows, the conditions as applied, and actually, as a matter of fact, it is greater than, not greater than or equal. It's not equal, it's all greater than. And we said that you need to have at least one of the rows greater than. You could have the rest equal, but here the conditions for all the rows are greater than. So now, once you have the system like that, basically all you need to do is to redraw the equations now in terms of x, y, and z, and then we start the iteration. So we'll go here for x, first iteration is equal to 10 minus, now y is 1, plus z is 1, divided by 3, and this will give me 3.33. Then we'll go for y, the first iteration was equal to 5 minus 2x, which is 3.33, minus z, which is 1. We have only one solution to z so far, divided by 10, and this will give me minus 0.27. Finally, your z is equal to minus 1 plus x, which is 3.33, plus 2y, which is 2 times minus 0.27 divided by 10, and this will give me an answer of 0.18. So that is my first iteration. Let's see the second iteration and see how much the difference, how much the error going from the first to the second iteration. So we'll go for x, second iteration. Now this is my initial guess now has been replacing the 1, 1, and 1. So x of the second iteration is equal to 10 minus y, which is minus 0.27, plus z, which is 0.18 divided by 3, and this will give me 3.48. Compare this with this, so they are very close to each other. Let's go for y, second iteration, which is 5 minus x. Now x has an updated value, 3.48 times 2 minus z. Z will use the value from the previous iteration, 0.18, divided by basically 10, and this will give me minus 0.21. Again, comparing this to this, they are very, very close to each other now, as opposed to the previous time when we see that the answer deviate significantly from the previous answer. Finally, z of 2 is equal to minus 1 plus x, which is 3.48, plus 2y, which is minus 0.21, divided by 10, and this will give me 0.21. Again, very, very close to this. So it's clearly now, when I rearrange the equation, the system is basically converging.